All right, our next speaker is Jan-Willem van de Meent. Jan-Willem is an associate professor at the University of Amsterdam and the co-director of the Amsterdam Machine Learning Lab. He's also an assistant professor at Northeastern University. He's done a lot of work in probabilistic programming. He was one of the creator of the Anglican language. He's also, I think, the lead architect for Probabilistic Torch. And he's done a lot of work in the questions that relate to modularity in probabilistic programming languages. He is one of the authors of the textbook, An Introduction to Probabilistic Programming, that many people here have mentioned already, and is also, like Vikash, a founder of the the International Conference on Probabilistic Programming. Today is going to talk about thinking compositionally about inference. Welcome, Jan-Willem.
Thanks, Jean-Baptiste, for that introduction, and also thanks to Xavier for organizing this event. It's been fantastic, I think, to be in the same room with so many of you and be able to kind of exchange ideas. So today I'll be presenting work by Heiko and Babak and Sam and Hao and Eli, who are my students. They're kind of spread out over kind of Amsterdam and Northeastern these days. And I think I'd like to start things off by just reflecting a little bit, if I can get the clicker to click. All right, so this is work by Heiko, Babak, Sam, Hao, and Eli. And I'd like to start things off by kind of thinking a little bit about where we are in kind of AI research today. And if you've been paying attention to kind of, you know, your Twitter feed or kind of general news, you'll realize that kind of this is really the spring of kind of scaling and deep learning. We've seen models emerge like PaLM, which are trained on like 500 billion parameters, and on every conceivable task under the sun for which Google engineers could get data. And these kind of really large language models are then sometimes capable of almost miraculous results. Here is the model asked to explain a joke about kind of an eloquent whale who has taught kind of, you know, the TPU team to communicate between two different pods. And to explain that joke, you need to understand that TPUs are Google's tensor processing units, that they're organized in pods, that pods need to communicate, and that whales also live in pods and communicate. And, you know, the language model can actually explain this type of joke flawlessly. And I think we as an AI community don't understand when this works and when it doesn't, but when it works, it's magical. And you know, you can also do things like generate images from text. And I think what's particularly impressive here is that you get a certain amount of compositionality. If you ask for an image of a wombat with a backpack next to a waterfall, holding a walking stick, staring at a distant mountain, you know, you get a scene with those 7 elements together, which kind of suggests that if we just train on kind of all of the data on the internet, some amount of kind of compositionality kind of does emerge from the data. And that's really led kind of, I think, AI researchers at large to kind of ask this question, like, okay, so is actually all you need for AI a bigger model, a bigger data set, more training? And I think this is kind of, you know, summarized in kind of this influential essay by kind of Rich Sutton from a few years ago called The Bitter Lesson, in which he essentially says, listen, in AI research, we're always trying to design custom models, but then eventually something simpler and more general that leverages more computation ends up outperforming kind of our carefully thought out approach. And so, you know, maybe we should start embracing that. And I think that in certain domains, like images and text, where we can kind of organize a massive amount of kind of, let's call it parallelized graduate student descent, I think kind of the bitter lesson is true, and it's maybe not so bitter. It's actually bittersweet, right? What we see is that a certain amount of abstraction does kind of just emerge if you train things on more data, and that's wonderful. At the same time, right, it's still not clear whether kind of just scaling up models and then adapting them to a particular task is really the most promising way to actually solving problems. And a good example of that is a blog post by Jacob Buckman, who's a student at Myla. So he asked himself the question, can I get GPT-3, which is one of these large language models, to play chess? And you know, his approach to doing this is almost embarrassingly simple. He feeds like a transcript of a chess game to the language model, and then he asks the language model to generate the next move. And what actually happens is that, you know, the language model plays a passable opening of chess for the first few moves, then starts doing things that are not really sensible to a chess player, and then eventually proposes an illegal move. And so this is both a win and a fail, right? Like it's a win that like the model can do this at all. That kind of by training data you found randomly on the internet, you can kind of sort of get this model to play chess. At the same time, if you're really interested in playing chess, and that's kind of the problem you're trying to solve, maybe the way to go about it is not adapting a model that was trained on random data that you found on the internet, right? You might need a more specialized model and a more specialized data set. And that's really kind of the question that, so to speak, keeps me up at night, right? So I think the AI community at large is going to continue scaling up these models to more parameters and bigger data sets, and that work will happen whether I contribute to it or not. The question that I would like to answer is, how can we really scale up the number of problems that we can work on as a research community? So how can we make these models more adaptable to specific domains? And there, kind of in my mind, the biggest success story from deep learning research is really AlphaFold, right? It's this kind of fairly kind of intricate network architecture that takes an amino acid sequence as an input and produces an estimate of a 3D structure, which is really one of the arguably grand challenges in molecular biology. And they've made a dent in this, right? With, you know, a big team and a large amount of resources, but maybe not even that big a team and that many resources compared to kind of how hard of a problem it is. And so the lessons for me, kind of, that I try to take away from deep learning research are that, you know, gradient descent has turned out to scale much better than we could have given it credit for. Like, the fact that this scales to models with 500 billion parameters is really an impressive feat. I think the other lesson to take away is that actually model engineering scales somewhat well. Right? A sufficiently dedicated group of people can figure out how to take, you know, a genetic database, a structured database, somehow turn this into a feature set that we feed into some big neural network, we cycle it through a few times, and then out pops a structure, and this actually works. But, you know, it's maybe not the most intuitive way to go about adapting your models to particular applications. And so when I kind of think about kind of what's next in AI research, you know, I think about applications in healthcare, things maybe like autonomous vehicles, and most importantly, things in science and engineering, where really what we would like to understand is, you know, how much domain knowledge should we integrate into our models? If we're analyzing data from the Large Hadron Collider, like Ganesh was doing yesterday, then, you know, you do want a good kind of model. Like, we have the standard model of particle physics. It can make predictions to 8 digits of accuracy. You know, you don't want to start with a blank slate model. On the other hand, you also don't want models that are brittle, right? Like, once you start making too many model assumptions, maybe in a kind of self-driving kind of car scenario, you may not have kind of coded kind of certain events into the model that you need to be able to account for. Now, the other thing we want to do is be able to kind of generalize, reliably generalize. And when we don't generalize, we at least want to make sure we don't make overconfident predictions. So I've been thinking about kind of what techniques are needed when for kind of some amount of time now. And me and my students, we try to keep ourselves honest by kind of working on techniques on a spectrum kind of tasks where sometimes maybe you need fairly kind of general architectures with weaker assumptions, and sometimes you need stronger assumptions. And so that ranges from kind of modeling of health records, which we do with transformers, to kind of tasks in kind of planning and robotics, which we largely do with graph neural networks, to kind of more tasks in simulation-based modeling, where maybe you have some known dynamics in the form of kind of differential equations. And so this talk will mostly be about that part of the work, but I do try to do work in these other spaces to understand how things connect. And that's really kind of what this talk is about. I think what I maybe try to figure out as a probabilistic programming researcher, and what kind of my students are trying to figure out, is, you know, how can we take kind of techniques from different subdisciplines and make them fit together so that we can start building, you know, the next 700 models for AI domains. And so this number 700 is of course not random. It's a reference to what my kind of PL friends tell me is a seminal paper in the programming languages community by Peter Landon. It's called The Next 700 Programming Languages. And Peter kind of starts off this paper by saying in a slightly different way, I will paraphrase, that kind of a programming language is really kind of two things. It's some set of core operations or abstractions, And then it's some syntax for kind of composing these operations together into a program. And, you know, sometimes we might be preoccupied with this kind of second thing, how we kind of write a program. But really, the core abstractions are kind of equally important, if not more important, in terms of allowing us to actually kind of do the operations we want to do. And when we think about those core abstractions in deep learning, right, it's really kind of about a kind of differentiable programming model that has emerged. And they're kind of, right, the core operations are automatic differentiation, tensor calculus operations, and I think some layers. Like most of us would not like to implement an LSTM from scratch because, you know, we would do it in a way that would have bugs. And what we've seen is that this programming model has been really successful. I think, you know, in deep learning, almost novice students can start experimenting with network architectures and objectives kind of within a week of starting, because, you know, we've succeeded at kind of capturing these kind of things at a high enough level of abstraction that if you somehow somewhat get the idea of what a convolution or an LSTM is, you can start integrating it in your model, even if you couldn't write down the exact kind of equations on a whiteboard. And so what I've been doing since maybe about 2016 is trying to figure out kind of how modern deep learning fits together with probabilistic programming. And there, I think the picture that has emerged for our group is that, you know, it's really kind of like the intersection of deep learning and importance sampling that is most fruitful for thinking about kind of how to scale inference in probabilistic programs. And we've seen some other kind of talks about this, right? Vakash has talked about this, Gunesh has talked about this, right? Really what is, I think, emerging in our field is this idea that we can train neural networks to accelerate inference, and in particular, that, you know, if you then use kind of importance sampling as the base strategy for doing inference, that you get something that's quite flexible and adaptable. And so kind of later on in this talk, I will really talk about kind of how we can make that approach a little bit more modular and composable. How can we design a language for kind of inference programming? That's a term that I think was coined by Vakash once upon a time. So how can we design kind of programs that denote different inference strategies? And how can we do this in a way where if we chain together operations, we're confident that we're computing in our importance weights and gradients correctly? Okay, so in order to kind of get through this, let's kind of review what amortized inference is. So those of you who were here to, like yesterday, will have heard kind of Gunesh talk about this as well. Right, so amortized inference is essentially the idea of treating kind of a model, a probabilistic program, as a stochastic simulator. And I think kind of in the context of the work I'm interested in, you know, what's relevant here is that that's most of science and engineering, right? Almost all of science and engineering has some form of prior. Let's say we're doing an epidemiological model, so maybe these prior parameters are infection rates. Then there's some model that makes predictions about kind of infections and case counts, and then there's kind of some output of the model, like a prediction about case counts that you can compare to data. And the idea in amortized inference is now, can we train a neural network to learn a Bayesian inverse to this model? So can we have, you know, some form of program that's parameterized by a neural network that takes data as input and returns a prediction about kind of the unobserved parameters. And in order to do that, we have to turn both of these things into probability distributions. So we're going to assume that this denotes some joint probability over data and our latent parameters. And then according to Bayes' rule, we have a posterior. That posterior is intractable, so that's why we're going to train this model to approximate this posterior. And here we have a data distribution that we can only sample from and kind of this approximation to the posterior. And now the kind of key idea in amortized inference is that we're going to somehow train these models so that this distribution becomes as similar as possible to this distribution. And the other thing that we're often interested in, and this is something that maybe, you know, like we've always kind of incorporated into our work, is can we train this model from data? So maybe this model itself has a bunch of optimizable parameters, and so we would like to make the predictions about data from this model as similar as possible to the data distribution. Now, there's a lot to say about amortized inference, and we've actually heard quite a bit about it. Today, I'm really going to talk about one particular take on amortized inference, which is kind of the intersection between amortized inference and importance sampling. And the idea here is that we're going to do inference in a way that's a little bit different from the kind of mainstream way of doing variational inference in both, I guess, the AI community and the probabilistic programming community. Typically, when we talk about variational inference, we see it as synonymous with, for minimizing a callback-Leiber divergence, and a callback-Leiber divergence where this variational distribution sits on the left side and the actual posterior sits on the right side. What we're actually going to do when we're doing importance sampling is, well, this is not always true, but I'm going to pretend it's always true, is actually swap these terms around. So what we're going to do is minimize the KL divergence between the posterior and the variational distribution. Now, the reason that this makes a difference is that the KL divergence is not symmetric. And when you now try to compute the gradient of this divergence, what you see is you're taking a gradient with respect to the parameters phi, and these parameters phi are the parameters of the variational distribution. And you're taking the expectation with respect to the posterior, which means that you can take this gradient and you can pull it into the expectation. And that's actually computationally quite convenient. What's not so convenient is that you now have to generate samples from the posterior. Let's pause for a moment to think about what this means. We started by saying we have some model. The posterior is hard to calculate. We would like to approximate it. So we're going to train some variational distribution or proposal to approximate it. But now, to train the variational distribution, we need samples from the thing that we couldn't approximate in the first place. So you could argue that this is a terrible kind of strategy for kind of doing variational inference. But it turns out not to be so terrible. And the people who discovered it was not so terrible are Bornstein and Bangio, who discovered this in the context of something called reweighted wake-sleep methods. And then a couple of years later, people in Frank Wood's group, led by kind of Toine Anglais, kind of realized that you could apply this to probabilistic programming. And so what's the key idea? The key idea is that you can approximate samples from this distribution using importance sampling. And this means that you're going to sample from this variational distribution that is easy to sample from. And you're then going to calculate an importance weight. And the importance weight is in some sense a correction factor. It tests if your sample is overrepresented or underrepresented in your variational distribution relative to the model. And once you have that importance weight, you can calculate a self-normalized estimator. This means that you take the weight and you divide it by the sum of the weights, so they sum to 1. And then you compute the weighted average of your gradient. Now, there's some statistical problems with this. And in theory, this shouldn't work because this estimator is very biased, particularly if you don't have a lot of samples. In practice, it does work. And I guess my intuition for why it does work is that you create this kind of virtuous cycle. You use importance sampling to get some samples from your posterior. They might be bad samples, but then you adjust your proposal to kind of mimic that kind of bad approximation to your posterior. Then your proposal next time around, as long as it has improved, gives you better samples from your posterior, which allows you to get a better gradient estimate, which allows you to get better samples, which allows you to get a better gradient estimate. And so in a lot of cases, this actually does converge. And what's actually quite key is that it doesn't rely on some of the kind of things that standard variational methods and variational autoencoders rely upon. In particular, your generative model doesn't have to be differentiable. And you did hear kind of Gunesh mention this yesterday as well, right? Like if you have a kind of really big simulator written in 1 million lines of C code, you don't want to completely re-implement this in a language that supports automatic differentiation. And so being able to deal with a non-differentiable model is quite a big benefit. The other reason you might want to do it is because sometimes you have discrete variables in your model, and those are also not differentiable. Okay, so for me though, kind of the real opportunity here is that now that we've kind of coherently connected importance sampling to variational inference, we can actually start experimenting with other importance sampling algorithms. And this is something that you heard Nicolas Chopin talk about yesterday, right? There's an incredible amount of kind of importance sampling algorithms that have been developed in the statistics community. And you can now ask the question, if I apply kind of a better importance sampler, do I get a better gradient estimate, which allows me to get kind of a better proposal and therefore an even better importance sampler kind of at test time? Okay, so one example of this is something called amortized population Gibbs samplers. And this is kind of something that we developed a couple of years ago. And in this particular problem, we were interested in problems such as this one. Like, suppose you have a video and you're trying to figure out what are the digits in this video and how are they moving. then you have a task at the level of a data set where you're trying to understand what digits look like and how they move. Then you have a task at the level of an individual instance, which is which digits are in this particular video. And then you have a task at the level of single frames, which is where are kind of the objects that are in the video in this frame. And there's a kind of classic problem when you try to do something like this, which is that it's not so easy to take a neural network and just spit out all of those variables. And the reason for this is that, if you know where the objects are, then it's relatively easy to get a representation of what they look like. You can just put bounding boxes around them, average over all frames, and then, run that through some neural network. What's also easy is if you know what the digit looks like, you can kind of find it in a particular frame, and so you can get the bounding boxes. But if you have to do both together, you kind of have to implicitly solve one task before you solve the other task using a big neural network, and it turns out that neural networks are not that good at that. So the classic solution to this problem is to iterate. You update the object representations given the positions, then the positions given the object representations, and you go back and forth between these two until your algorithm converges. The problem here is that this was kind of historically only computable in very limited classes of models where both the prior and the likelihood belong to a special class of kind of exponential family distributions. And so now the modern kind of amortized inference take here is, can we replace this with some neural proposal and can we learn that? And so the answer is yes. And once you do this, you end up with a completely unsupervised model that learns your generative model for data. And actually, at test time is pretty computationally efficient. This takes maybe 10 samples and 5 of these kind of update sweeps in order to converge for kind of a typical video. And at the time, it was kind of competitive with kind of the best, LSTM-based kind of attend, infer, repeat kind of style kind of approaches. Okay, so let's now talk about kind of how we can take a step back from these particular examples and kind of generalize from them. And there really kind of the question becomes about kind of language design. What are kind of key abstractions and ways of composing abstractions that allow us to kind of develop these types of algorithms? And this is in some sense the question that Nicolas Chopin asked yesterday, right? He said, listen, probabilistic programming is great, but I would like to develop my own algorithms. How can I do this? Well, I think this is a partial kind of answer to this question, though I don't know if it's ready for Nicolas's graduate students. That's maybe another question. Okay, so what's the question here? Well, here's kind of the algorithm that I just kind of illustrated at a high level as we show it in the ICML paper from a few years ago. And you have a few lines here where there's kind of weight computations and gradient computations. And what this describes is a known class of samplers in the statistics community. It's called a sequential Monte Carlo sampler. But what's unique is that it's an amortized one. We learn the proposals. And so kind of at the level of kind of, if you're a trained statistician, this is kind of something where you would say, well, this is a novel algorithm, but it really combines kind of known building blocks. On the other hand, if you're trying to train a graduate student, everything they need to know to implement this algorithm, like it takes a graduate student, I think, about 2 years to do this, maybe 1.5 years to kind of understand it, and then a half a year to get the bugs out. And so the question here is really, can we design some form of language that allows you to write down this inference algorithm in a way where at least it's supposed to do the correct thing, and then later you can figure out if it's efficient. And so the thing that we came up with is basically a language of combinators. So these are functions that accept programs as input and produce a different program. And where this language picks up is in some sense where kind of the work by Christine and also kind of people in Sam Statton's group and Hong Seok Yang kind of leaves off. We're going to assume that we have some form of program. We're going to call that a primitive program, and we're going to assume that our programming language colleagues have produced semantics for kind of whatever language program you can write in this base language. And we're going to assume that this program does a bad job at doing inference. It does something called likelihood weighting. And then we build on top of this. We define operations that implement basic importance sampling kind of building blocks. And for example, that is using samples from one distribution as proposals for a different distribution, or using non-equally weighted samples and doing a resampling step where you select particles with probability proportional to their weight, which means that you're going to replicate high weight samples and with high probability eliminate low weight samples. And then there's also move operations where you apply some form of transition operator and then you update the weight accordingly, and I'm not going to go into the details of exactly how that works. Okay, so the key kind of thing here now is, can we design these operations in a way that ensures that you're computing your importance weights correctly? And in order to do that, we decided to build on a core property known as proper weighting, and that's kind of something that, it's an idea that's been around in the statistics community for a while, but it was formulated maybe in the most kind of digestible way by Christian Nassef and co-authors in 2019. And here the idea is that if you have some sampler, let's call this sampler capital P. Actually, let me start here. Let's say that we're trying to compute some function h, and we're trying to compute its expectation. And we're trying to compute its expectation with respect to some target density, and that in our case is the posterior of our program. Then what proper weighting says is that you can generate samples from a sampler, which are a weight and a value, and you can multiply that weight by the thing that you were trying to compute. And that then, you should be equal to this expectation that you were trying to calculate up to an unknown constant of proportionality, and that's typically the marginal likelihood. Okay, so why is this property important? Well, what's nice about proper weighting is that it gives you a way to reason compositionally about correctness. If your incoming samples are properly weighted, and you can prove that after applying an operation they're still properly weighted, then actually it doesn't matter exactly how you generated the incoming samples, because you can now move to the next step and say, my samples are properly weighted, let me now consider the set of operations that I can apply that will still kind of keep them properly weighted. And so this allows us to kind of just write down some operational semantics for each of the operations in this language and basically define relative to which density kind of your program is properly weighted as you kind of build this up. So we've implemented all of this in our kind of experimental probabilistic programming language called ProbTorch. It's also been independently implemented in Pyro by one of their developers, and our kind of students have now been working with those developers to make sure this is integrated into Pyro. This has been a long time coming because Pyro has a lot of bells and whistles, and so there's more edge cases suddenly to consider, like things like plates. But the implementation should now be coming this summer. And we'll be providing some workbooks and examples. So if you're a statistician and you would like to start tinkering with this, this is something you could take a look at. Okay, so what does all of this give us? Well, really what we've now done is we've taken this kind of description, which is math. It's a kind of computations that compute weights and gradients. And we've turned it into this type of description. And if you just kind of squint, and that's what I'm going to do at the level of this talk, right? Like one doesn't look substantially more or less complicated than the other. But what's really happened now is that this is a high-level algorithm description. It's basically saying I'd like to start by applying a proposal to something, then I'd like to move things around, then I'd like to resample them. And you can just chain these operations together now, and they're always going to produce one of these properly weighted importance weights. So the only thing you have to worry about is what's the right sequence of operations, not how do I implement the importance weight calculations or the gradient calculations. And so this now kind of like allows people to start working with these things at a higher level of abstraction. Okay, so I'll start wrapping up. So really what's kind of for us has emerged in, I guess, period of the last kind of 4 to 5 years is this idea that maybe we can productively combine differentiable programming with probabilistic programming, and in order to really make that work, we also need some form of inference programming. And you've heard of kind of several instantiations of that idea in the last couple of days. And so I think our instantiation here is really kind of centered around importance sampling and learning kind of neural proposals for kind of importance samplers, so you get this kind of virtuous cycle. And what we've seen today is that we can now design a language that will kind of allow users to specify their own importance samplers. What I haven't really talked about today is that you can also allow users to specify their own objectives. So I lied a little bit when I said that we're only minimizing this inclusive KL divergence. There's actually generalizations of this as well that you can use. Okay, so I guess kind of finally, I'd like to kind of wrap up with maybe a little kind of call to arms. Right, I think that, if you're an AI researcher in this room, what we've been extraordinarily successful as an AI community is organizing ourselves around big ticket problems, right? Like deep learning had this kind of AlexNet moment where suddenly we could do image classification really well. And then I think in computer vision, kind of people have really identified key challenge problems that they can compare against. Same with language modeling. And now what we're starting to see is kind of really remarkable and sometimes magical progress in these problems. But these are only a dozen problems, right? There's hundreds and hundreds of more problems that we could be solving. And some domains that I've worked on are biophysics and neuroimaging and epidemiology. Some domains that people in AmLab are working on are in astrophysics or kind of molecular design. I also have colleagues working on computational fluid mechanics. This is just kind of like a random grab bag of problems that we could be working on. And I think we should be working on. Let's figure out kind of what are the kind of areas where by bringing AI to the table, we can make a dent in ways that people haven't made before. And that means that I think we need to kind of start thinking even more broadly about what probabilistic programming is. We think, we've heard a little bit about learning surrogate models in the last couple of days. We've heard a little bit about program induction, but I think this is also relevant in molecular design. We maybe need to think about kind of how can kind of AI researchers formulate their intuitions about how to do search in search spaces that are not very smooth. So maybe the program actually defines the search strategy rather than kind of the model that you're trying to do inference over. And finally, I think there's a kind of an emerging area where people are thinking more and more about the intersection between neural networks and differential equations. And I think that's going to become more and more important in the next few years where, really we need to think about, can we use neural networks to approximate solutions to ODEs? Can we learn ODEs? Like, can we learn a model that is like a coarse-grained description of some dynamics that are really expensive to compute? Because I think if I look at a lot of these domains, right, like gravitational waves, computational fluid mechanics, a lot of these problems, actually quantum chemistry as well, involve incredibly expensive kind of simulations. And we just can't do enough of them to kind of do the search problems that we're trying to do. And so I think we're going to have to figure out what role kind of probabilistic programming can play in helping us kind of develop approximations to these very expensive simulations. Okay. I'll stop there. So once again, this was work by Heiko and Babak. Both Heiko and Babak are close to being on the market. So if you're kind of looking to hire someone, you should come talk to me. And then at Northeastern by Sam and Eli, and actually by Hao, who is also kind of on the market. So, I have several students, on offer. And actually, if you're interested in coming in the other direction, we are hiring at AmLab at all levels, at the faculty level, at the postdoc level, at the PhD level. And so, of course, I'd love to hear from you if you're interested. All right, I'll stop there. Thank you.